Okay, this is the little video that you guys wanted on SHM. I don't usually go over SHM, it's not a particular problem, but we will be doing some problems on SHM and you do need to understand it. So I'll start by just talking about, not my best circle in the world, but not too bad. We'll talk about this little reference circle that we use. Now, this is a mathematical tool, and what you visualize is a point on the circumference of that circle going round in circular motion. So this is at a constant speed. So we would have an omega here, or a v, which would be equal to omega a if a is the radius. So that's a constant speed. Now this is a mathematical tool that helps us with SHM. In SHM, if this was our spring, and it starts at that point, that's its equilibrium point, and that's its lower point, so the spring basically bounces up and down, then there's a point at which the spring is in the middle position, equilibrium point. Now, we could have had the spring on a horizontal surface, sort of thing, you know what I mean, where it goes backwards and forwards like this, with maybe two springs and doing SHM, and then that would be the equilibrium point. The thing to remember about the reference circle is it doesn't have to be oriented in the same sort of plane as your object. You just have to remember it's your tool, and I use this angle, we'll call it theta, as my angle, and therefore if I'm representing this point, if I'm looking at the vertical plane as my projection screen, then it's my vertical plane tells me the displacement. So if on my vertical plane we call this the equilibrium point, then the displacement is how far away from the equilibrium is your object, i.e. how far is the mass away from the equilibrium point. And our circle, which is just a mathematical tool, the projections vertically here onto the screen give you all the information for displacement, velocity and acceleration that you want. The circular motion is not representing, well, let's just say this mass going up and down on the spring is not travelling in a circular motion, but this circle is able to give us the information if we project its movement just in one dimension. It's a really interesting relationship. So if we project this point as it goes round in a circle onto this screen, it will display the motion of the mass going up and down on the spring perfectly. So it displays SHM perfectly. But only one component. And like I said yesterday, when you do complex numbers, you'll find out that you can use the complex E equals I theta in a lot of your equations to do this, and you'll just use the real part. But you'll get to that. Ignore it for now. For now, just recognize that this point going round, if we project it onto a screen, so we're just getting one part of its motion, it displays SHM perfectly. So in trying to figure out where our mass is, because it's quite a complicated movement, and it's complicated because the force is proportional to distance, so the force is changing, so the acceleration is changing. That's complicated. Now, if I want to know the projection as that point goes round in a circle onto this vertical screen, then that's easy. So if we're going to call the distance away from the equilibrium d, then that's just a sine theta, but theta equals omega t, based on when the clock starts, a sine omega t. Now omega's in radians. It's radians per second. So radians per second times seconds gives you radians. Alright? So this is a point where we get some confusion too. So a sine of an angle, so the sine of 30 degrees, is equal to 0.5. Right? Now the sine of 30 degrees as a radian is also equal to 0.5. But if you put in 30 degrees, you better have your calculator on degrees, And if you've put in 30 divided by 57.3, approximately half a radian, then you better have your calculator on radians, because you don't want the sign of half a degree. Alright? So it doesn't matter what you put in here, as long as you know what you're using. So when you've gone from radians per second times seconds, you're in radians. So you better have your calculator on radians, unless you convert it. So hopefully I haven't been too confusing in my explanation, that this circle is just a tool to give us the distance a mass doing SHM is away from its equilibrium point, and that somehow this circle, when we project onto a screen to give just the one dimension, will give that information perfectly. So the velocity is equal to omega A, but again we only want the vertical component in this case. So the velocity might be in this direction at that point, but we only want the vertical component, and the vertical component, that's theta also. So the vertical component is going to be equal to the velocity, which was just that big vector there, times the cos of theta. Now V equals omega A, so the vertical component of the velocity is just omega A cos theta. And the acceleration, well, acceleration is equal to V squared over R, which is A, but that's omega squared A squared over A, so that's equal to omega squared A, right? But that's towards the center like that, right? And again, we only want the vertical component. So you can see again, the vertical component will be omega squared A times the sine of theta, because that's theta. So it's omega squared A, which is the length of the long vector, but it's just the sine of theta. Let's change those into omega A cos omega t, omega squared A sine omega t. Now, that's a negative because the velocity was going up, positive is up, the acceleration is down, so acceleration must be a negative. So that's how it works. You can just do the calculus, of course, on the d to get the v. So differentiate the d with respect to t, and you'll get the v. Differentiate the v with respect to t, and you'll get the a. So that's how it basically works. Hopefully that little discussion on also over here on radians and degrees helped. If you had decided that this was your angle, alpha, instead, then to get all these correct, the sine would become a cos, this cos would become a sine, and the sine would become a cos. Those are the alternative equations. What does confuse some people with this business is the fact that we do these projections onto a vertical screen and use this angle. Like I said, we could have used alpha. And then when they see something horizontal, like a pendulum or a spring with a mass going backwards and forward horizontally, they then think we can't use this reference circle in the same way. The fact that we're using these vertical projections makes no difference. These vertical projections are going to give us the distance away from equilibrium, and the fact that this might be horizontal, this spring up here, this distance here, x, if you like, or d, or whatever you want to call it, is still just the distance away from the equilibrium, and this full distance is still just the amplitude. So the fact that our reference circle uses a projection onto the vertical, we don't have to change anything. We don't have to turn it upside down or anything like that. So we always use the reference circle that way, whether we're dealing with an object going up and down in SHM or sideways, backwards and forwards in SHM. Hopefully that has sorted it out for you.